An incident response analyst spots a critical digital trace during a high-stakes breach investigation. They found the exact moment an attacker logged in. But when the incident commander asks how they found it, the explanation falls apart. The workflow usually looks something like this. The analyst ran a script they found online, passed the output through a specialized parsing tool, clicked through a few unrecorded manual filters, and eventually spotted the anomaly. The actual methodology is usually buried in a messy, unversioned text file saved directly on the analyst's desktop, filled with what we call magic queries. Look closely at this string. It searches for event identifier 4624 in a Windows security log. The syntax is exact, but there is absolutely no context explaining why this search is relevant to the broader investigation. Relying on tribal knowledge to interpret these raw strings creates a severe bottleneck. If the analyst who wrote the query is off shift, the rest of the Security Operations Center is left staring at meaningless text. You cannot build an automated threat detection pipeline on top of personal cheat sheets. It also makes onboarding junior analysts incredibly difficult, as they have to independently reverse engineer the logic behind every inherited search parameter. As long as digital forensics operates as an artisanal craft executed by individuals, rather than a structured, documented process, security teams will fail to scale their responses against modern threats. The discipline requires a structural overhaul. Digital forensics needs to move away from isolated guesswork and transition toward codified intelligence. This is the goal of DFIQ. The framework takes a chaotic tangle of individual data points and organizes them into a clean, predictable hierarchy. It is built to be system agnostic. The logic defining how to investigate a threat is independent of the proprietary quirks of any specific vendor's dashboard. DFIQ achieves this by strictly separating the overarching investigative intent from the ground-level technical execution. It maps all of this institutional knowledge into a standardized, YAML-based format. This makes the investigative steps machine-readable, easy to share across organizations, and strictly version-controlled. By standardizing the syntax, security teams can construct and contribute to a global catalog of clear investigative questions and their corresponding analytical approaches. The magic query problem disappears. With DFIQ, every technical search is explicitly linked to a documented high-level purpose. At its core, forensics is the process of answering a specific question by uncovering digital traces and interpreting them in a reproducible way. At the pyramid's bottom is the digital trace. Moving up, the analyst interprets that raw data as a technical action. An attacker logged on. This answers a tactical question. How did malware persist? Finally, at the peak, it addresses the high-level scenario. What happened here? Isolated SIEM queries fail because they only provide that bottom layer of raw traces. They lack the top 3 layers of context. DFIQ serves as the connective tissue. It structurally forces the analyst to map their raw findings all the way up the specific dependency graph. If you cannot map a log file back to the overarching incident, the data is practically useless for explaining the scope of a breach to stakeholders. Let's test this framework on a practical, ambiguous scenario. An analyst notices active DNS requests originating from a web browser process on an endpoint. The anomaly arises when the analyst checks the endpoint itself. They find 0 local browsing history matching those active network requests. Without a structured process, an investigator might guess they are looking at malware performing process hollowing. But guessing is dangerous. They need to prove it structurally. DFIQ provides a specific question node for this scenario. Was an incognito browser used? Instead of jumping to a query, it forces the investigator to identify the required telemetry. In this case, CrowdStrike process rollup events. Before a single line of code is written, the investigator has a clear record of exactly what raw data is required. Once the data source is identified, the framework dictates the processor needed to parse it. For this example, we use Splunk. Now, DFIQ reveals the specific query logic mapped to this processor. It directs the analyst to search the logs for the syntax command line in disable databases. That string, disable databases, is the precise command line parameter Google Chrome uses under the hood when a user launches an incognito window. Now, compare this approach to the isolated text file we saw earlier. This specific query is now permanently mapped to its intended purpose, making it instantly understandable for any junior analyst. But DFIQ goes a step further by enforcing rigorous boundary setting. It uses explicitly declared covered and not covered tags. This approach explicitly states that it only covers Chrome installations on Mac, Linux, and Windows hosts running a CrowdStrike agent. The documentation also strictly defines what it does not cover, such as renamed Chrome processes or other Chromium variants like Edge or Brave. Defining what a search tool cannot do is just as important as what it can. It prevents investigators from assuming they have full visibility and falling victim to false negatives. Moving from isolated text piles to machine-readable YAML creates a set of instructions that external software can interpret directly. Because DFIQ documentation explicitly tags required data sources, a tool like Yeti can ingest a high-level scenario and see the entire graph of dependencies needed to answer it. Yeti passes these data requirements to a collection tool like GRR, which automatically gathers the specific artifacts identified in the YAML file. Once the collection is complete, the system uses the mapped query strings to automatically queue the required analysis in a platform like TimeSketch. The analyst's workflow changes. They stop typing out ad hoc queries and start reviewing the automated structured results produced by the codified graph. Abstracting the investigative intent away from the raw code creates a reusable, version-controlled ontology. This lowers the barrier to entry across the board. Junior analysts no longer have to rely on hidden tribal knowledge to run an effective investigation. Open-source frameworks like DFIQ allow the global security community to collaboratively distribute and constantly refine this threat data. An investigation's validity depends on whether the conclusions reached can be proven consistently to an external auditor or stakeholder. By treating forensic processes as codified intelligence, security operations ensure their investigations remain structurally explainable, highly reproducible, and scientifically sound.